Okay, so this is chapter 2, question 17. Here, a car's velocity is a function of time given by v of x of t, v sub x of a t is equal to alpha plus beta t squared. Alpha is 3 meters per second, beta is 0.1 meters per second cubed. And in part A, what we're supposed to do is calculate the average acceleration for the time interval from t equals 0 to t equals 5 seconds. So let's start with that. In part A, our goal is to calculate the average acceleration. And in general, the way that we calculate the average acceleration, which I'll call A, is that we take the delta V over the delta T. When I say the delta V, I mean that it's a change in the velocity, and the delta T is a change in time. So you could call the change in velocity the final velocity minus the initial velocity. And then you could call the change in time the time final minus the time initial. And here we already know what time final is. Our time frame ends at 5 seconds, and our initial time is 0 seconds. But what we don't know is, at the initial time, what was the velocity then? And then also at the final time, what was the velocity at that point? We don't know those things. So we're going to have to do a little bit of work here to figure those things out. Let me just fix this. So to figure those things out, what we're going to do is we're going to look at the velocity function, which is given to us in the problem. The velocity function is here. Velocity as a function of time is equal to alpha plus beta t squared, where alpha is 3 and beta is 0.1. So why don't I just take that velocity function, write it down here, and I'll plug in the numbers from alpha and beta. So it'll be 3 plus 0.1 t squared. So that is our velocity function. I'm going to highlight it so that way I know, and we just remember that that's the important one. And what I want to do is I want to figure out what was the velocity initial. Now the velocity initial would be the velocity function evaluated at time 0. And I want to know the final velocity, which would be the velocity function evaluated at time 5. So let's see, velocity function evaluated at 0 would be 3 plus 0.10 squared. And velocity function evaluated at time 5 would be 3 plus 0.15 squared. For the first one, the 3 is going to be the answer because this term goes to 0. For the second one, it'll be 3 plus, this is 25, this is going to make it 2.5. 3 plus 2.5, it'll give you 5.5. The units for this is in meters per second. Here, this is meters per second. Okay, so now we're able to come back to this formula here to calculate our average acceleration. It'll be 5.5 meters per second minus 3 meters per second divided by 5 take away 0. So that's going to work out to be 2.5 over 5, which is 1/2 or 0.5. The units for acceleration will be meters per second squared here. And then that's the end of problem A, part A. Part B, we have to calculate the instantaneous acceleration for t equals 0 and t equals 5 seconds. The key word in here is that in part A, we're looking for instantaneous acceleration. In part B, we're looking for instantaneous acceleration, whereas in part A, we were looking for an average acceleration. The average acceleration, you saw the formula for it. It was like the change in velocity divided by the change in time. For instantaneous acceleration, It's basically the average acceleration formula, but you take the limit as delta t approaches 0. So that's what would get you the instantaneous acceleration. Um, More importantly, uh, you can summarize the idea of instantaneous acceleration as just saying, well, you get it from the slope of the velocity function, or of the position function. And if you can take the derivative of we could take the derivative of the velocity function, what we could do is we could get the instantaneous velocity. What we could do is we could get the instantaneous acceleration here. So what we're going to do now, our plan is to take the velocity function, take the first derivative of the velocity function, and that'll give us the acceleration function that we need to find the instantaneous acceleration. Okay, so we're going to say, all right, we're going to say, okay, we're going to take the first derivative of our velocity function, and that'll give us our instantaneous acceleration. The first derivative of the of the velocity function is going to give us, see, like here, this 3 constant disappears once you take the first derivative. And then here, this is a power rule terms. You take the 2, multiply it against the 0.1, and then the exponent goes from 2 to 1 here. So this is going to give us 0.2 t. This will give us the acceleration at any given time, the instantaneous acceleration at any given time. And if we wanted to find the instantaneous acceleration at t equals 0, we would plug 0 into this acceleration function to get, and whatever it gives us is the instantaneous acceleration at that point. If we wanted to find the instantaneous acceleration at this different time frame, at 5 seconds exactly, at that moment in time, what we would do is we would say, okay, to find the acceleration at that moment in time, I'm going to plug a 5 right in here, and then this is going to spit out an answer to give us the acceleration at that point in time. Okay, so to find the acceleration, the instantaneous acceleration at time frame 0, I'm going to basically call this function my a of t function, and I'm going to evaluate it at 0, and that's going to give me 0.2 times 0, which is 0. Acceleration is given in units of meters per second squared. So at time frame 0, at the instant that time is 0, acceleration is 0. And if I wanted to figure out what the acceleration is at precisely at 5 seconds, I'd do 0.2 times 5, which would give me 1.0 or 1. So the acceleration there is 1 meters per second squared. So we're done with part B. In part C, we need to draw the velocity as a function of time graph, and then we also need to draw the acceleration as a function of time graph, and then we need to chart that between t equals 0 and t equals 5. So in part C, I'm going to be using Desmos to graph this, but I kind of just want to make a plan. When I want to draw the velocity of time with respect to time graph, basically I'm going to be charting this. But of course, in Desmos, I'll write the t as an x, so that way the Desmos will show it to me properly. And then for my acceleration versus time graph, I'll be charting this. And then the domains are going to be limited to between 0 and 5. So that way we can do exactly what they're asking us for. And so we've got Desmos here, and we're going to just chart this. This is going to be the velocity graph is going to be 3 plus 0.1, and I'll call it x squared. And then I'm going to limit it to the domain between 0 and 5. Okay. To zoom in a little bit here. So that's our velocity function. And now we're going to chart our acceleration function. And then we're also going to limit it to the domain between 0 and 5. So these two graphs here together are our answer for part C.